So in the last couple of lectures, we tried to understand why 1 to 100 nanometer this range is important and why it is important to study the nanoscience and nanotechnology. Then we have seen that depending upon the dimensions, okay, how many dimensions are present at the nanoscale, there are different types of nanomaterials, and we have seen that there are 4 types of nanomaterials are present, that is a 3-dimensional, 2-dimensional, 1-dimensional and 0-dimensional. Now in this lecture we are going to see 2 important effects which are observed only at the nanoscale. Okay, so because we are reducing the dimensions of the material to the nanoscale, so what effects are going to origin, what things are going to change at the nanoscale in case of nanomaterials, that we are going to see in this lecture. So as I said, the 2 important effects are, the first effect is quantum confinement effect. Okay, so the first effect is called as quantum confinement effect, and second is called as surface area to volume ratio. Okay, so surface area to volume ratio of the nanomaterials. So these 2 effects we are going to see in this lecture. So let us start with quantum confinement effect. Now as far as materials are concerned, okay, materials are made with large number of atoms. Okay, large number of atoms are present in the material. So in case of bulk material, if you consider a bulk material, we have seen that the number of atoms are very large, and as we are decreasing the size of the material, the number of atoms started to reduce. Okay, so in case of bulk materials, if you remember, the number of atoms which are present in the material, they are in the range of 10 raised to 20 to 10 raised to 22, 25. These number of atoms will be present in the bulk material depending upon its size. So if this large number of atoms are coming together, okay, so when atoms, recall that when atoms are brought together in a bulk material, okay, so there are a very large number of atoms are present in the bulk material, and when they are coming together, so their number of energy states increases. Okay, so energy levels, they start to overlap on each other, okay, because they are close enough to each other, okay, so that their electrons started to share with each other to form the bonds. Okay, and because of this, the number of energy states increases substantially. Because the number is very huge, the number of atom is very huge in bulk material, okay, the distance between the energy levels is so small that we consider it as a continuous band of states. Okay, so we call, for bulk material, we say that we have valence band, we have conduction band, okay, in case of semiconducting bulk material. Okay, so if you consider a band, then it is nothing but continuous arrangement of energy states, and because the energy states are very high, the distance between the energy states is too small, so that we consider it as a continuous band. Okay, so this is what is happening in case of a bulk material. Okay, okay, so what happens if we reduce this bulk material to the nanoscale. So that then there is an effect which is called as quantum confinement effect started to originate when we reduce the size of the material from bulk to nano. So as you can see, the first point, the quantum confinement is the spatial confinement of electron hole pairs. Okay. So when we are talking about individual electron and hole, okay, then these are the individual charge carriers. Electron is a negatively charged carrier, hole is positively charged carrier. But consider the electron and hole, they are remaining together, they are not separated with a large distance, so they are present in pairs. So when the electron and hole is present in pair, then it is called as an exciton, then it is called as a excitons. Okay. So quantum confinement is the spatial confinement of electron hole pairs, that is excitons, in one or more dimensions within a material. Okay. So what is quantum confinement? Is a confinement of electron hole pair, is a confinement of exciton. So exciton which are present in the material, they start to confine, they started to confine. Now in how many dimensions they confine? It depends upon the degree of confinement. If the material is confined in one dimensional, then the quantum confinement will be observed in only one dimension. Okay. If the degree of confinement is two dimensional, then the quantum confinement is observed in two dimensional. Okay. If it is observed in three dimensional, then the quantum confinement is observed in three dimensional. Okay. So it depends which type of material we are talking about, one dimensional, two dimensional, three dimensional, or zero dimensional. Depending upon that, the electron hole pairs, they started to confine. So the quantum confinement effect is observed when the size of the particle is too small to be comparable to the de Broglie wavelength of electrons. Okay. So when this quantum confinement effect is started to be observed, only after a particular size. It is not like if the size of the material is just below 100 nanometer, we started to observe quantum confinement. No. Okay. For each material, depending upon the type or nature of the material, this confinement will be observed at different dimension. Okay. And that dimension is so small compared to the de Broglie wavelength of electrons. Okay. It means de Broglie wavelength of electron is belongs to Bohr's atomic radius. Okay. So if the size of the material is started to reduce below Bohr's atomic radius, then this quantum confinement effect is started to observe in the material. To understand this effect, we break the words like quantum and confinement. Okay. The word confinement means to confine the motion of randomly moving electron, to restrict its motion in specific energy levels. Okay. That is discreteness. Okay. Suppose as I already discussed with you in the last lecture, when we are talking about the confinement of electrons, I give you example that you are standing in a room, and if the room is free enough in all direction, you are able to move in all direction. But if the size of the room is exactly with the size of your height and your width, then you are no more able to move. Okay. So in that case, in a zero dimensional material, the degree of confinement is in three directions. Okay. So likewise, the confinement means to confine the motion of randomly moving electrons, to restrict its motion in a specific energy level. In particular energy levels, the electron is unable to move because the energy level become discreteness. Okay. and the quantum reflects the atomic realm of particles. Quantum is representing the size is very small, where the quantum physics started to involve. Okay, so what let us try to understand what is this discreteness. So see the figure which is given in the below. As you can see on your left hand side, there is a valence band and conduction band is available, and there is a band gap which is represented with Eg. Okay, and as you can see that the bands are continuous. The valence band is also continuous, the conduction band is also continuous. Okay, continuous means because it is a bulk material, large number of energy levels are available, they are overlapping to each other, the distance between the two energy level is very small, so that we can consider it as a continuous. So this is a continuous band. What is a discrete band? What you can see on your right hand side. So you can see that on your right hand side the energy levels are not continuous, even in the valence band and even in the conduction band. Even in the valence band, you can see there is a space between the two lines. The space between the two lines is representing that there is a gap. So the gap is representing that the electrons are not allowed in that energy levels. Okay, so electron can either be present in any one of these three energy lines, energy levels, or below the continuous energy band. Okay, so it is a discrete means there is a the space between the energy levels is got increased, the space between the energy levels has got increased. So this is one effect which is observed in the quantum confinement. Okay, there is a second effect is also observed in the quantum confinement effect. What is that effect? You can see that on your left hand side, okay, the bands are continuous, but the energy, the band gap Eg is represented with a continuous red line arrow. Okay, so red line arrow is representing a distance between the valence band and conduction band. So that band gap has been increased when the material is reduced from a bulk semiconductor to a nanocrystal semiconductor. Okay, so when the material is reduced from bulk semiconductor to nanocrystal semiconductor, then you can also observe that the energy band gap which is shown on the right hand side for the nanocrystal material is bigger. Okay, so it is represented with the green arrow. So the length of the green arrow is now higher as compared to the length of the red arrow. Okay, so you have to keep in mind that when the quantum confinement effect is observed in the material, two things especially we can observe. When the bulk semiconductor material is reduced to the nanocrystalline semiconducting material, then we can observe the two things. One is the continuous energy levels, they become discrete, they no more remain continuous, they become discrete. This is one effect, one thing. And second thing is what? The band gap is increased. So the band gap of the material which is present in the bulk semiconducting material, okay, now it has got increased when the size of the semiconducting material goes to zero dimensional quantum dot material. Okay, so as the size of the particle decreases, okay, last point of this slide, so the size of the particle decreases till we reach a nanoscale. The decrease in the confining dimension makes the energy level discrete. Okay, so energy level become discrete, and this increases or widens up the band gap, and ultimately the band gap energy also increases. because the number of atoms reduces, okay, from the bulk, when we are reducing the size of the material from bulk to nano, the number of atoms reduces, so the energy levels reduces, so the energy level become discrete. Instead of bands, it become discrete energy levels, and because the energy levels become discrete, the band gap of the material has increased. Okay, so you have to keep this in mind if you want to discuss anything about the nanomaterial. This quantum confinement effect is very important. So uh, can we observe in actual practice this confinement effect, quantum confinement effect, can we observe in actual practice? Yes. So that is we can discuss in this slide. So here you can see the relation of quantum dot size with the band gap. Okay, let's discuss because the quantum confinement effect is very strong in a zero dimensional material, okay, as compared to three dimensional material. So we are taking a special example of quantum dots where the degree of confinement is 3. In all three dimensions, the material is at the nanoscale, so the electron is confined in all three dimensions. That is example of a zero dimensional material, which is also called as a quantum dot. So is there any relation with the size of the quantum dot? Okay, so in the last slide, as I shown, the nanocrystal of semiconductor. So nanocrystal of semiconductor, especially zero dimensional nanocrystal of semiconductor, is also called as a quantum dot. Please keep in mind. Okay, so now if the size of the quantum dot, nanocrystal semiconductor quantum dot, is changed, what happens to the band gap? Will it change? Okay, so the answer is yes. Okay, so how will it change? So you can see the band gap of spherical quantum dot is increased from its bulk value by a factor of 1 upon r square. Okay, where r is the particle radius. Okay, so it is inversely proportional. So as the radius is going down, the band gap is going up. Okay, and it has of course it has a special condition. It is only possible when the single particle, because it is based upon a single particle solution of Schrodinger wave equation, and that is valid only for the r which is less than the exciton Bohr radius. As I already told you that the quantum confinement effect is observed only when the size of the nanoparticle is reduced below exciton Bohr radius. So below that radius, if the size of the particle is reduced, then this effect is observed. Okay, and because of this effect, what happens? The band gap has got increased. So how we can understand this? So let us see. Quantum dots are band gap tunable by size. Okay, so quantum dots are band gap tunable by size. What does it mean? It means that if we want to change the band gap of the quantum dots, we have to change its size. We can engineer their optical properties and electrical properties. Once you understand this, okay, so you are able to engineer its optical and electrical properties. Means how much band gap do you want? Accordingly, you can tune its size of the quantum dot. Okay, so you are able to do that. So smaller quantum dots have larger band gap. Of course, because the size is going to become smaller and smaller, the number of atoms which are present in the material, they become more lower and lower, and because of that there is an increase in the quantum confinement effect, and because of that increase in the quantum confinement effect, the band gap is become increased. The absorption and illumination spectrums are blue shifted with decreasing particle size. Okay, for example, so you can see here in the image there are three quantum dot semiconducting quantum dots are shown. One is red colored, which is bigger in size. The radius is bigger in size. The second one is green in color, and the third one is the blue in color. As you can see, even in the red there is a quantum confinement effect, but its a band gap is smaller. Its a band gap is smaller, so that it is emitting red colored light. Its a illumination spectra is observed in the red color. So the quantum dot with this size is, you can see the color of the quantum dot is red. Okay, if I read, if the material is same, now the material is same, please keep in mind the semiconducting material is same, let us say PBS, lead sulfide. So if we are talking about lead sulfide quantum dots, okay, and if it is emitting red in color with this size, and if further we reduce the size of PBS, lead sulfide quantum dots, then the color is no more remain red. The color has got shifted from red to green. Okay, now what you can see, the color of the quantum dot is green. Why? Because its a band gap has got increased, because we have reduced the size. If you further reduce the size of the lead sulfide quantum dots, then you are able to see blue colored quantum dots. So the material is same, but now you have three different band gaps. You have the same material with the red in color, the same material with green in color, the same material with blue in color. Just what is the difference? The difference is in the size of the quantum dots. So this is the beauty of quantum confinement effect, which you can able to actually engineer at the nanoscale. Okay, you can engineer the optical and electrical properties at the nanoscale with this quantum confinement effect. Okay, so now you have same material with different colors. Okay, in bulk, because the number of atoms are too high, the band gap is constant, it has only one color. But the same material has multiple colors when we go to the nanoscale. Now let us try to understand the second effect, which is called as surface area to volume ratio. Okay, so in this effect, let us try to understand how the surface area is going to change when we are going from bulk to nano. Okay, so let us try to understand this based upon this cube. Okay, so in this figure you can see in the first cube is a single cube. Okay, is a single cube. What is the length or width or height or width and length of this cube is 1 meter. Okay, so all x direction, y direction, z direction, all this in all direction the size of the cube is unique, is a 1 meter. Okay, so if we try to calculate its area, then you can see that because it has a 6 faces, it becomes 6 meter square. Okay, so this is the area of the cube when the size of the cube is 1 meter by 1 meter by 1 meter. Suppose I cut this cube in two directions. One is the vertical middle of the cube. From the center of the cube, we are cutting this cube in two directions. One is vertical cut and second is horizontal cut. Okay, I did two cuts. One is a vertical cut, second is a horizontal cut, which is passing through the center of the cube. Then what happens? Then we have got 8 cubes. We have got 8 cubes with now size. What is the size of each cube? Is half meter by half meter by half meter. Okay, now the volume is still same. Please check this. The volume of the cube is still same. What happens with the area? Now the area has got increased. You can do the calculation, and now you can see that you have 8 cubes. So now the area has become 12 meter square. Area of the surface. Surface area become 12 meter square. Okay. Again, okay, if I cut it more, if I make more slices of it as shown in the below cube, okay, now the number of cubes is become 27. Number of cube become 27, and if we try to calculate the surface area of these 27 cubes, then it is coming 18 meter square. So basically what we are doing, we are reducing the size of the cube by keeping the volume of the cube constant. Okay, because we are talking about the ratio, so suppose the volume is we kept constant, okay, and we are just changing, we are just reducing the size of the cube, we observe that the surface area has got increased from 6 meter square to 18 meter square. Okay, okay, so this is a very basic fundamental example with which we are trying to understand how the surface area is increased when the size of the cube is reduced. Okay, let us see that the total surface area increases as you cut the block into smaller pieces, but the total volume is remain constant. So you have to, the volume is still same. Okay, we are not changing the amount of material, we are just changing the size of the material. Okay, and then you can see the surface area has got increased. Now let us see an actual example of this, and we can understand how it is going to change at the nanoscale. Now suppose we are taking a cube of gold. Now the size of the cube is 1 centimeter by 1 centimeter by 1 centimeter. Okay, so we have a gold cube. Okay, so volume of the gold cube is 1 centimeter cube. Okay, but its size is 1 centimeter by 1 centimeter by 1 centimeter. Now below this cube you can see what I have written. So total number of atoms, how many number of atoms are present here? 5.9, around nearly 5.9 into 10 raised to 22, because it is a bulk material, is a big crystal of gold. So the number of surface atoms which are present is 1.2 into 10 raised to 15. These number of atoms are present on the surface. So if we take these two numbers and try to calculate the percent of surface atoms to total atoms, it means what? How many number of atoms, how many percent of atoms are present at the surface, okay, compared to the bulk, okay, compared to the total number of atoms. So you can see the number comes in the range of 2 into 10 raised to minus 6. Okay, so 2 into 10 raised to minus 6 number of atoms, percent number of atoms are present on the surface, and all other atoms are where they are below the surface atoms, they are in the bulk of the material. Now suppose we started to reduce the size of this gold cube, and again keep in mind that the volume, okay, is reduced to 1 nanometer cube. So the size of the cube has got reduced from 1 centimeter by 1 centimeter by 1 centimeter to 1 nanometer by 1 nanometer by 1 nanometer. So we can call this as a gold nanocube. Okay, so in that case the total number of atoms which are present in the gold cube is, they are nearly 108. Okay, because now the size is very small, 1 nanometer by 1 nanometer by 1 nanometer. So in that size only 108 number of gold atoms can come together. So how many number of surface atoms are present? They are nearly 84. So if we calculate the percent of surface atoms to total atoms, then it is a 78. This is a very huge number as compared to the bulk gold cube, because in that case the percentage is in the range of 10 raised to minus 6, and now here the percent of surface atoms is in the range of 78. Okay, so you can see that large number of atoms are present on the surface. Now we are talking about that there is a very a huge increase in the surface area of the nanomaterial when we are reducing it from the bulk. Okay, so if the material is already in the bulk, with size, will it change? Of course, yes. Simply see the example of gold nanoparticle. Okay, because now see, we are taking the gold nanoparticles, both so we are taking two gold nanoparticles. One is with a radius of 12.5 nanometer, and second spherical gold nanoparticle is of radius of 5 nanometer. Now both are in the nano, but one gold nanoparticle has a size, what is the radius? 12.5 nanometer, and second gold nanoparticle radius is 5 nanometer. So you have two gold nanoparticles, both are in the nano region, but still you can see, is there any change in the change in the surface area? Yes. So in case of gold nanoparticles with radius 12.5 nanometer, you can see it contains approximately 4,000 4,80,000 atoms, and the surface atoms, they are approximately 48,000. Okay, so if we again try to calculate how many percent surface atoms are available, then you can see 10% atoms are available on the surface. Okay, 10% atoms are available on the surface. But the same gold nanoparticle, if we reduce its size to 5 nanometer, then 25% atoms are present on the surface. So what you learn from this, that when you are reducing the size of the material from the bulk to the nano, okay, then the number of surface atoms which are present on the material is become very high when we go to nanoscale. Even in the nanoscale, if the size is still, we are changing the size of the nanoparticle, still there is a huge difference in the number of surface atoms which are present on the surface. Okay, so that is what the beauty of the nanomaterial. These two effects you have to keep in mind always, that when you are taking a material from bulk to nano, two things happen. Never forget these two things. One is what? There is a introduction, there is a observation of quantum confinement effect. Okay, it started to introduce, it started to observe in the nanoscale. And what is second effect? The second effect is increase in the surface area of the nanomaterial. Okay, these two effects are going to change a lot when the material has started to reduce its size from bulk to nano. Now here we are taking we are trying to understand why it is important if the surface to volume ratio is changed. Is it going to matter? So of course yes. Okay, so let us first try to understand. Okay, let us first try to understand what is surface. Okay, if you think about the term what is a surface, okay, then you realize that what is surface. Basically, what is surface? How to understand a surface? So a face which is going to separate two media. Okay, a face which is going to separate two media. For example, if you are sitting in your house, if there is a desk or table in front of you, please observe the surface of the table. Okay, so the surface, that is the face of the table, the upper face of the table, is what it is doing. It is separating two media. The upper media of the table is air. The downward media of the table is its a material. It will be anything like wood or marble or anything. Okay, so the atoms which are present on the face, they are separating the two media. Okay, one is air or liquid or anything, and second one with its neighboring atoms. Okay, so this is a surface. Okay, so if the surface is changing, what we are expecting to change? Let us see. The first point is the greater amount of substance comes in contact with the surrounding material. As I said, because the surface is the face which is separating the two media. So if the surface is higher, then what happens? A large amount of substance, it started to come in contact with the surrounding material. The second point is the surface atoms have unused electrons which contribute to chemical reactions. Okay, now please uh, try to imagine, okay, the example which is I am going to share it here now. Okay, now suppose I make a chain of 10 students. Okay, we all are in a class. Okay, I am in front of you, we all are in a class, and suppose among the class I take 10 students. Okay, and I make a chain of 10 students in such a way that each student has to share his hand with his friend. So each of you have two hands, so you are sharing your two hands. Okay, and you are just making a chain with your friends. Okay, so now we have a chain of 10 students. Okay, and if I come to a middle student with any number, like 5 number student or 7 number student or 3 number student, and I am trying to shake hand, hello. If I say hello and if I am trying to make a shake hand, he is unable to shake hand with me because already the two hands are engaged with their friends. Okay, but so this is what in between. So these are the situation of atoms which are present in between the faces. But suppose if I go to the first student or to the last student of the chain, where it's a one hand is still open, and if I ask him, let us shake hand, hello, how are you, that student is able to shake hand with me. Why? Because his only one hand is engaged with his friend to make the chain. The second hand is still remained open. So with that hand, he can easily shake hand with me and interact with me. But the students which are in between, they are unable to interact with me. So this is what our second point is representing, that the surface atoms have unused electrons, okay, which are on the surface, which are on the top. So on the top there is no another atom is present, so that electrons are not shared with other atoms because there is no atoms are available on the top, but all other electrons are shared with the neighboring atoms. Okay, so these surface atoms have unused electrons and they started to contribute to chemical reactions. So the chemical reactivity of these nanomaterials is get increased. What is third point? The surface area dependent properties of nanomaterials get changed. Okay, so if you are taking some examples where for some applications, okay, where the surface area is really playing a role. Okay, so in that case, as I said, the surface area dependent properties of nanomaterials get changed. Okay, so the properties which are depends on the surface area, they get changed as we are changing the size of the material, because you have seen that in the this slide you have seen that even the gold nanoparticle has a 12.5 nanometer is radius, 10% atoms are available on the surface, but when we are taking the same gold nanoparticle with 5 nanometer radius, then 25 number of atoms are present, percent of atoms are present on the surface. So it means there, if the gold nanoparticle has some property which belongs to its surface, then its chemical reactivity of 5 nanometer gold is higher than 12.5 nanometer of gold. So in that sense, we are talking about point 3. 4 is the reactivity or solubility is a surface area dependent property. Okay, chemical reactivity or solubility, okay, they are surface area dependent properties. They will get changed as the size of the material has got changed. The 5th point is this results in better catalysis since a greater proportion of material is exposed for potential application. Okay, so this is very important, the last point. As an example, this is what the example of point 5 is. The bulk gold, the gold when it is in bulk size, it is not catalytic, okay, but the gold in nano size works as catalyst. Okay, so this is the surface area dependent property of nanomaterial. Okay, so I already told you that the properties of the material, they started to change when we go from bulk to the nano. So this is one of the property, chemical reactivity. Okay, so the bulk gold, it is no more it was not reactive when it is in the bulk size, but when the same gold is reduced to the nano size, then it shows the catalytic properties, catalyst property. Okay, here is a small example just for your imagination, that so if you take a loose sugar, okay, which it is also called as a granulated sugar, and second is a sugar cube, you can also think about crystals of the cube, single crystals of the cube. Okay, that is a much better in example. Okay, which is also called as a khadi sakhar in Marathi. Okay, so if you take a big crystals of a cube, okay, and a granulated sugar, and you take the same amount of sugar in weight, okay, take same volume of the water and try to dissolve it, and then see which will dissolve faster. Okay, so which will dissolve faster. Okay, so that you can think, and you can imagine that because the granulated sugar are small in size, okay, as compared to the single crystals of sugar, okay, then you can easily see that the granulated sugar will dissolve faster than a single crystals of the sugar. Okay, so because of these two important effect, that is the quantum confinement effect and change in the surface area to volume ratio of the material, okay, the properties of the material become size dependent. Okay, for example, the chemical properties, that is the reactivity or catalysis, they will get changed, okay, with the change in the size of the material. The thermal properties, that is the melting temperature, it will no more remain same. So the melting point of bulk gold and the melting point of a nano gold, they will be different. Okay, they will not be same. The mechanical properties, that is the adhesion or capillary forces, they are also get changed because they are again related to the surface phenomenon of the material. The optical properties, that is the absorption, scattering of light, they will get changed. Electrical properties, that is the tunneling current, is a new kind of current what we observe when the material goes to the nanoscale. We started to see the tunneling current. Okay, and in the magnetic properties, new effect which is called a super paramagnetic effect has been started to observe. So at the moment I am just giving you a small feel that how many properties of the material can be changed. Okay, but in the next semester we are going to see in detail how the chemical properties are changing or why the optical properties are changing, how the electrical properties are changing, and because of this change, can we see the different can we make different kinds of devices at the nanoscale which are not which cannot be functionalized at the bulk scale. Okay, so that is what our aim when we are going to see the physical and chemical properties of nanomaterials in the next paper. But here just you have to keep in mind that these two important effects, that is quantum confinement effect and surface area to volume ratio effect, they are basically going to change at a very large with a large factor, and because of that the different properties, that is chemical, thermal, mechanical, all optical, electrical, magnetic properties, they are going to change when the size of the material is started to reduce from the bulk to the nano.